So thank you for being here. And if you attended my other talk, this first session, you are in the wrong place, as I told you. Yeah. So you didn't follow my instruction. Anyway, so yeah, I have been working on this hash chemistry stuff. So now, after two excellent talks about real chemistry, if you are craving for the nonsense coming from computer scientists, here it is, right? So the key idea of the hash chemistry that I already presented in the first afternoon session was to make the open-ended system that is minimalistic in terms of computational stuff. And this conference that I presented two such variations of hash chemistry. But anyway, so this is the original motivation, open-endedness. Many of you already heard about it. So it's now it's very actively discussed in the AI machine learning community as well. Thanks to Ken Stanley, Joe Lemon, and Lisa Soros. They put up this idea like 7 years ago. Now, if you go to AI conferences, some of them are actually actively talking about this. And the issue, again, this is the same slide. You will see the same jokes, the slide again, many times. Yeah. So we basically try to create an open-ended artificial chemistry system by using the bottom-up approach. Instead of talking about, the higher level mechanisms, we want to create a artificial chemistry system entirely from bottom-up so that you can see some continuous production new forms. And then the idea that we are exploring for the last couple of years is the cardinality leap. So instead of having the set of possibilities well-defined for the individual level, if you allow a system to form higher order entities, mathematically, this will automatically give you the infinitely larger possibility space. So the big challenge, this is a new slide that I didn't put in the first presentation. The big challenge is that if you are creating the artificial system, artificial life, artificial chemistry system that allows the entities to form higher order structure, is how do you evaluate their success or failure? So typical evolutionary computation, evolutionary robotics approach would be that you have fitness rule, like if you're evolving biped robots, you measure distance, how far a robot actually walked. That's a pretty straightforward evaluation stuff that you still have lots of papers talking about how to control a robot. But what happens if you have two robots working together? What happens if you have 10 robots working together? What happens if you have 1 million robots or maybe fighting against each other? What does it mean? What is the success of that kind of higher level entity? We simply do not have the computational tools to evaluate that. So the demonstration I published 5 years ago is called hash chemistry. It's a very, very easy model that anyone can program in 10 minutes. So here you have some kind of the distributed particle system. Originally, we use a two-dimensional system, and you grab any localized cluster and put it into the hash function. Instead of designing any meaningful mechanism, you just give up. Okay, evaluating the higher order structure at the multiple different level will be too complex. So let's give up and then just resort to the God that everybody has access to, right? Hash function can take any kind of the data and they give you the one value, deterministically created value as a return value. So we can use this as the generic multi-scale higher order structure evaluator. And depending on what kind of the fitness, quote unquote, value the hash function gives you back, you just decide what to do. And then this is the dynamic simulation. You have seen that in this afternoon session, sorry. This is the original work that we did 5 years ago. The hash function kept applied to a bunch of places, and then just that repetitive application of hash function everywhere in the space, you see this kind of dynamic evolution process going on. So this is cool. And we measured how many different types, combinations of particles successfully replicated over time. So the left one is just the number of particles that emerged. So there is only the finite number of sets, 1,000 particles. Quickly, the evolution will explore all the possibilities individually. But if you look at the combinations of those particles, it kept going up linearly over time. So this is the number of different combinations of particles that successfully replicated. So this is good. So the cardinality leap actually did work, at least in the very primitive demonstration phase. And we also did a little bit of statistical testing about how the average number on the right and the maximum number of the particles that work together to replicate, they actually kept increasing over time, although more rigorous statistical tests shows that maximal number of particles, they actually were bounded. And in the meantime, the average number looked like it's an unbounded growth. But this kind of mixed result. Is it really the unbounded growth of complexity in terms of size of the entities? We were not quite sure 5 years ago. Okay. So these are the unsolved problems in the original paper back in 2019. And the computational cost in the original hash chemistry was very, very large, especially because I was not really using optimized code. I was a heavy Wolfram Research Mathematica user. This was actually simulated in Mathematica. Takes days, right? And also the lack of the unbounded growth of complexity in terms of maximal number of entities. So we want to have the more unbounded system at a much faster computational speed. So that's the rationale for this non-spatial hash chemistry. I decided to give up another thing. Let's give up space. Although the Seth Bullock mentioned that this morning, anything related to life has to be spatial. I'm actually giving him the counter argument. Maybe space is not necessary. Yeah, I mean, we are talking about artificial life. We are not talking about the biological life. So you can imagine the universe that does not have a space. Can we still have some kind of meaningful dynamics? And here's a very, very classic, almost, artificial chemistry system. Instead of having a spatial domain, you just assume that everything that is contained in the universe is in this multi-set. So this L is a list of all the existing molecules, so to speak. Each molecule is a multi-set. Here you see orange, blue. I'm colorblind half, so I cannot really see the colors. But you see different colors of particles are contained together. They tend to act as a single entity, no matter how many particles are involved. And then the algorithm is still very simple. You just grab two molecules randomly from this population, apply the hash function, each of them, they're going to produce values. Like this one produces 0.93. This one also produces 0.932476. There's a slight difference between them. So you choose whichever side actually produce the higher value as a winner. And the winner is going to be replicating, and then its offspring is going to be put back to the population. The loser may die, especially if the length of this list gets really long. So there's a carrying capacity, obviously, to maintain the computation at a reasonable size. That's it. You just pick two molecules, let them compete, and the winner is going to survive, loser is going to die. You repeat this many, 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 many times, and then something interesting happens. Okay, and we actually have the publication, full paper publication published in the ISSS, the CEC, Congress on Evolutionary Computation. So if you want to read the full paper, please take a look at the archive version as well. It's available from here. It's kind of hard to argue this kind of artificial chemistry papers to the audience who are mostly evolutionary computation people. There are lots of question marks floating in their head. Okay, so here's a detail of the algorithm that I already explained that you already understand. This is how it looks like. I still miss the spatial model because spatial models are so cool to visualize. Non-spatial version, it's very difficult to create engaging animation, but here you go. So what you're seeing is on the right, you see the histograms. What kind of entities are currently present in the population? As you see, almost all the time, just one type dominates at the top. There are many, many variations, but they are basically negligible. But you see here, the plot on the left is the it's not quite a histogram, it's a curve, but it shows that what is the size of an entity in the current population. Initially, it started from just a single particle entities, but over time, now you see another transition. It keeps increasing, right? And I didn't really put any biases or anything. So here, you already understand the entire mechanism. You always pick two molecules, evaluate their hash values, and then let the winner replicate. And yet, this spontaneously happens. It's a magic. No, it's actually not the magic. It's a very simple mechanism I can explain, but this is already the good enough to demonstrate what is the power of the cardinality leap, which actually always goes up, if you simulate this longer. Okay, is that clear? It's a really, really simple artificial chemistry system. It's kind of awkward to say this artificial chemistry after 2 real chemistry talks. It's something that the computer scientist is going to dream. This is the chemistry. Yeah. All kind of the unrelated to, all things that are unrelated to the real chemistry. And here's the diagram required by the reviewers in that evolution computation conference. They required us to do the performance evaluation. I initially said, no, we are not going it, but we want to have a publication. We actually listened to it. Okay, we did it. The original version. This is non-spatial version, and then I presented cellular version earlier today. And there are 3 different versions, and then the vertical axis is the computational time, how much time you needed to run the simulation. And obviously, non-spatial and the cellular version get much, much easier to simulate. Again, I have to make this clear. This is not really a fair comparison. Those 3 systems are completely different system. There is no rigorous apple-to-apple comparison, but whatever reviewer requested, you have to do it. Yeah, so simply put, it's actually much faster. And here's the really interesting result. I'm going to summarize in the next 2 minutes. If you keep measuring how good the fitness became in this non-spatial version, the fitness went up continuously over time. So this is the time in the log scale. The vertical axis is how many digits the fitness value actually approached to the maximum value 1. 1 is absolute maximum, which is unreachable. Initially, the evolution quickly improves to the 0.99. Over time, it gets to 999, 9999. It keeps going up until it actually goes to the resolution limit. There is also a resolution limit. And this is the maximum fitness value and the average fitness value. In both of cases, thin red lines are the individual simulation. The black solid lines shows the average value. It kept growing over time. This was not observed in either the original version or the 3rd version I presented earlier today. And we also applied the statistical test about the average numbers and the maximum numbers of particles inside each successful molecules. It also went up. And both cases, maximum numbers and average numbers, after comparing 2 different mathematical models, bounded growth and the unbounded growth, they both showed the unbounded growth. So this is the proof that by conducting a statistical test, you have the better fit for unbounded growth model. So here, we did it. Yes. So this is a crazy simple artificial chemistry system, and we get rid of the space. And yet, you actually observe that most of the time, the average number of the particles included in the molecules actually keep going up. By the way, this is for those who didn't really attend my first talk, this is the cellular version, what it looks like. This is prettier, but unfortunately, this cellular version did not show that continuous adaptation over time, although it's much easier and more fun to watch. Yeah. So anyway, so here's a summary of those 3 variations of the hash chemistry model family. The original one had the individual-based evaluation mechanisms. All of them actually show the cardinality leap. The computational efficiency is much better for the non-spatial and the cellular one. Cellular one is very, very fast. The multi-scale ecological interaction between different entities were missing in this current version I'm presenting. Non-spatial version is just a collection of molecules. They don't really interact with each other, except for the pairwise competition. This is something I'm missing right now in this non-spatial version. Other ones, original ones and the cellular ones, they have the spatial interaction and the multi-scale, the non-trivial, the ecological interactions. So the key question I'm facing right now is that, this one is I'm presenting here. So apparently, just comparing those 3 different models, there seems to be a trade-off between the non-trivial multi-scale interaction between evolving the entities and the more meaningful adaptive behavior, specifically continuous improvement of fitness. So it seems to be that it's very difficult to satisfy all of them. But ultimately, what I would like to do, is to create another version that has all the check marks in all of those rows. We'll see how it goes. Wait for me in my presentation next year. So anyway, so conclusion, we get rid of space, and it got much faster. And also, we finally achieved the unbounded growth for both the average and maximal number of entities because of the absence of spatial pressure. If we put everything into space, there is definitely a density limit. So that always put the constraints. But if you have a non-spatial version, number or the size of entities completely open. So that's, that makes things a lot easier for A-Life system to grow longer and larger. Okay. And I already mentioned the limitations. So we want to include more context-dependent, non-trivial ecological interactions. And one thing I didn't mention here is that in real biological system, replication of longer molecules takes more costs because there are lots of the errors possible. I cheated here. If you got the winner, you have the exact replication done in one step. So if you embed everything into the more real biological settings, you need to have a mechanism to correct those errors. So that is another limitation. Okay, thank you very much. I'd be happy to take questions.